Hello, hello, good evening all.
Dr. Ajinkya,
Yes, sir.
yeah, how are you?
Yeah, good. Yeah, I'm fine.
So just we are
What
starting the
about you,
session.
sir? Yeah,
I'm good. I'm good.
yeah. Okay, so can I start? Hello.
Yeah. Okay. Good evening to everyone. Respected faculty members and all dear participants present over here. I hope you are having a wonderful learning experience. I hope you are having a wonderful learning experience in this ongoing 2-week online faculty development program on grid resilience and adaptive control evolution in power system, that is GRACE PS 2025, jointly organized by Department of Electrical Engineering, MNIT Allahabad, and Department of Electrical Engineering, NIT Patna. I am Navneet Pathak, and it is my privilege and honor to introduce our distinguished speaker for the session, Dr. Ajinkya, who is a renowned industry professional. We are delighted to have Dr. Ajink with us today and look from his expertise in this important area of different grid challenges for large scale renewable power plant operations. Dr. Ajink is a power transmission and distribution industry professional. He has earned his PhD from IIT Indore and currently serves as product engineering lead at L&T Digital Energy Solutions in Pune. In this role, he focuses on various control solutions for renewable energy plants. Dr. Ajink expertise spans technical product management, research and development in renewable energy management system. He has contributed to field through publication in previous prestigious international journals. In this session, Dr. Ajink will be delivering a lecture on topic different grid code challenges for large scale renewable power plant operations. Sir, we are truly honored to have you with us today. With that, I am request Dr. Ajink to kindly take over the session from here. Sir, the time is all yours. Thank you.
Yeah, thank you, Nolanji. I'll share the screen. Am I audible properly? Hello, my voice is
Yes,
clear?
sir. Yes, sir. Yes,
Okay,
sir. Audible, sir.
okay,
Yes, sir. You are audible.
okay, okay. So thank you, Nolanji. And hello, good evening, all. I'm Ajinkya Sonone, working as a product engineering lead in L&T, and in L&T there is a one business unit that is digital energy solutions. In that I'm working. In L&T, I'm leading the development of controller products like power plant controller, hybrid energy management system, and base energy storage system. So at the time of development, control is one of the aspect that we consider, but we also need to consider the grid code of a different region where that product is integrate the plant to the grid. Uh, I'm I'm okay. Able to see the screen, right? Hello,
Yes,
are you able
sir.
to?
Your screen is
Oh,
also
okay, okay,
visible.
yeah, yeah. Okay, okay, thank you. Okay, so I'm here to present and discuss what I have learned during this process on this topic, that different grid core challenges for large-scale renewable power plant operation. Throughout the presentation, the focus is on secondary controller, that is solar power plant controller, and the grid core requirement fulfilled by it. So first we go through what is DI and the major challenges of it. Then what is grid code and rules need to follow if you want to integrate the plant with the grid. Then the brief understanding of what is control hierarchy and the role of the secondary controller and the challenges of grid code. And at last, I will present the typical power plant topology for the large power plant. Large power plant controller means you can say in 700 megawatts or in gigawatts. That topology we will discuss, and the expected PPC operation to achieve the maximum power when that topology is implemented. So that is what we are going to discuss. Then what is DER? DER basically inverter interface DGs with renewable energy sources. So forces behind the evolution of DER is basically increase in demand of energy, then concern over fossil fuels, then more focus on energy efficiency, increase in awareness of greenhouse gas emission, development in DER technologies, and one more, yeah, increase customer demand for a highly reliable electricity. These are the few forces, these are the few reasons why DER is so popular. So as per the IEEE definition, DER is basically a sufficiently a smaller central generating unit which which allow interconnect at nearly any point in the power system. So when the DR integrated with the plant, there are few challenges like technical operation and regulatory challenges that we face. So there are technical challenges like variability and uncertainty. So all we know in renewable power plant, suppose it's a PV plant. In PV plant, when the radiations is change, there is a sudden change in radiation sometimes. So it may cause a sudden change in active power, and because of that active power there we can observe the sudden change in frequency, as well uh, as you know, active power and reactive power are indirect, they are coupled indirectly in weak grid system, so it will impact the voltage also. Then second major reason is reduce inertia. Whenever we are implementing the large power plant into the grid, it will reduce the overall inertia of the system, and uh, which leads to fluctuation in frequency. Then also whenever we want to implement integrate the power plant, grid code expect the advanced grid support function from that DR like FRT frequency, then voltage regulation. There is a weak grid challenges. These large power plant are basically located at remote areas. So if it is located at remote area, it means it has a limited transmission strength. Limited transmission strength means if it is located at remote area, it means it is far away. So transmission line is it is in means hundreds kilometer or 200 kilometers. So it increase the impedance of the system, and as because of high impedance, it leads to weak grid. And for small disturbance also we can change the we can observe the high change in voltage. Then there is a protection and control, because in large power plant there are number of inverters are available, 500 or maybe more than 500, 600, 700 like that. So for that we need protection coordination, and also we need the control, because power plant need to give set point to each inverter. So for that control is required. Then there is a operational complexity like communication and data. Then because as in the plant there are number of inverters, other than inverters there are number of asset like you can say if you want to monitor the transformer, then transformer is one of the asset. Then inverters, then PQM meters, then MFM meters, so then WMS meter, right? So these that controller or that plant need to communicate with all these assets. Then you should coordinate with the thousands of inverter. If there is a statcom in the plant, yes, it need to integrate with the statcom also. It should send the real-time set point to that set point to that inverter, and you also need to achieve the ramp rate as per the grid code. Then there are some regulatory complexities like system planning. System planning means whenever, okay, regulatory is send which provide the set point to number of plant available in each region, right? So it need to manage the power. So it will always plan based on the forecasting, what is the radiation forecasting, solar forecasting, and based on that it should provide the set point to the different part available in its region. So that is one of the complexity. Second one is the different grid code for different region. There are different grid code for KSA India like that. So it, so that large power plant, because it's a product, right? Same product is going in all the power plants, so you should maintain that different grid code also. Then there is a continuous update in standards of renewable penetration. As the renewable penetration will rise, that grid code all evolves, and if grid code is evolves, we need to update those standards or those grid code in that plant. Then need for testing, validation, and certification of the plant. Before that plant going to charge in the site, before that we need to test it in different software like PSSC, PSCAD. We need to validate that different test cases are performed based on the grid code, and when those test cases are acceptable, their results are acceptable, then the actual regulatory is giving permission to charge the plant. So that is one of the process and one of the regulatory complexity. Okay, then as it's a cyber security, yeah, cyber and communication complexity, that plan need to communicate with the SCADA, as well as it should communicate with the tertiary level, that is regulatory, because regulatory is sending set point to your plant, so it should communicate with that regulatory also. And also as there is a increase in cyber security risk in digital power plant. So these are the major challenges, and to overcome these challenges and to integrate the power plant into the grid, power plant must obey the grid code requirement defined by the utility grid operator. So what is grid code? Grid code is basically a set of rule book. It is a technical standard rules and procedure defined by the grid operator or regulator that govern how that plant should connect, operate, and interact with the electrical grid. Then there are few importance of the grid code. Like grid code mandates the power plant to maintain the grid stability. It mandates the plant to regulate the voltage as well as frequency. It ensures the reliable operation. Like it mandates that plant should have FRT, that is fault right through functionality. It should have protection functionality, so that it will increase the reliability of the plant. It should have facilitate the large scale integration. So as the grid code is if so consider the grid, there is no grid core, so each plant will operate independently. So it may create the oscillations in the grid. So there is a so grid code is so uniform grid code is required for all the plant, which should follow the grid code, and we should maintain or uh, increase the reliability of the plants. Then protection and power system equipment, protect and power system equipment. So that plant grid code mandates that plant should have protection and coordination technique which avoid the disconnection of any inverter or any asset because of small disturbance, and indirectly it should protect the asset, and it can safely integrate the power plant with the grid. Then it should enable the ancillary services from the renewables. So ancillary services like it should mandate that grid code is mandate the power plant to maintain the voltage and frequency, as well as suppose there is a HMS plant. So the expectation from which grid could expect from the HMS plant that it should have black start capacity, right? So black start capacity means whenever grid is not there, it should completely start the plant. So those services, those ancillary services it is expecting from the grid, and yeah, this helps replace the service once provided by those conventional power plant, right? Then future readiness. Grid code evolves to handle the DER and provide the roadmap for the DER to participate in smart grid and energy market. And yes, uniform standard. It should provide the uniform standards, uniform grid code to all the power plant. So these are the few importance grid code. Then these are the key components of grid code. Uh, like ramp rate control. It supports the active and reactive power through by implementing the ramp limiter logic. Then grid code should have frequency regulation to support the active power, again voltage regulation, power factor regulation. It should have fault right through phase function. It should have protection and coordination and communication and monitoring. Communication monitoring obviously required for data exchange and remote control because it need to communicate with the SCADA, Modbus, and it need to connect with the SCADA or regulatory through the communication protocols like Modbus, TCP, for example, etc. Okay. Then there's a control hierarchy. So actually, in the plant, there's a control like tertiary level, secondary. Okay, in the actually in the last power plant, there is a secondary level controller and primary level controller, and that grid code is basically applied to the plant, not to the secondary or primary level. Okay, so suppose this is a tertiary level control. So tertiary level control is basically you can say it is that set point to the secondary control is or to the plant is provided by that tertiary level control. Tertiary level control is a regulatory, or in India you can say it's the NLDC for RLDC, or for SLDC. RLDC is a tertiary level controller, like, right? So that tertiary level controller, okay, that each grid code cannot be fulfilled by these different level of controller because control levels are based on their speed of response and time frame. So you can say primary control basically you can say inverter. It should be a faster, its response should be in millisecond. Then there's a secondary controller, its response is in seconds to minutes, and there is tertiary controller whose response is in minutes to hour. So this tertiary controller will send set point to secondary level control based on its economic dispatch or generation forecasting. So each plant will receive the set point from tertiary level controller. Then is secondary level controller. Okay, whenever the new plant is getting implement, there is an agreement. That agreement is there are different type of agreement. Okay, so one of the agreements suppose that plant should achieve the set point active power set point, or active power set point receive from the tertiary level controller. So main aim of the secondary control is the to achieve the active and reactive power when voltage and frequency is within the band. But if voltage and frequency are not within the band, then that secondary controller should control the voltage and frequency. And if in that scenario, if it is not achieve to control the frequency, for example, if it is not achieving the active power, then it is acceptable. In that case, that secondary controller, that power plant tertiary level regulator will not apply any penalty to that secondary level controller. But if everything is under control, active power set point is there, radiations are also available, but that plant is not achieve the set point provided by tertiary level control, then yes, that tertiary level, then that regulatory will apply penalty to that plant. Then the secondary level controller send the set point to primary level controller. Primary level controller is basically inverter. So main aim of inverter is to achieve the set point received from the secondary controller, it should be faster. And the second, okay, if the secondary control is basically controlling the voltage and frequency steady state, but if there is a transient scenario like a fault, in that case primary level controller as per the grid code, it should enable the LVRT HVRT functionality to control the voltage or to stay connected to the grid. And then these all these measurements go back to tertiary level, secondary level and primary level, and based on that they will take the decision and send updated set point to each controller. Then all these controllers, or sorry, all these grid cores or maximum grid core achieved by power plant controller, and to achieve that power plant controller has two different operation modes or control modes, you can say, like active power mode, reactive power mode, power factor mode, then there's a frequency voltage drop and AVR regulation mode, and yeah, one more, that is the ramp rate control. So we'll go one by one. So first one is the ramp rate control. So ramp rate is essentially a speed at which generator can increase, that is ramp up, or decrease, that is ramp down the generation. So this is one of the grid code which needs to follow by each power plant. So the requirement is that grid code specifies that particular plant should ramp up and ramp down by provided ramp rate. Suppose the ramp rate is 10, okay, in usually that ramp rate is in Indian grid code, the ramp rate is 10% per minute. 10% per minute means if the rating of the plant is 100 megawatt, it should achieve the 10% of power, that is 10 megawatt in 1 minute. Okay, and in 1 minute, and the acceptable band means, okay, if it's a plant, right? So it's a plant, so it may possible in the plant, okay, whatever the 10% per minute is for the set point, but this is the ideal condition. But in actual in the plant there are the losses. Whenever we are injecting the active power, reactive power into the grid, the losses in the plant will increase. As the losses in the plant will increase, so controller should give higher set point to inverter so that it should achieve the ramp rate in 10% per minute. This is a practical scenario. So, and for that there is an acceptable band also. So acceptable band is plus minus 10%. 10% means if the set point is suppose 10 megahertz, same example, it should achieve in 60 seconds. So acceptable band is it should achieve that set point within 66 to 54 seconds. It should not cross this limit. This is one of the grid code. Okay, sorry. So the challenges are basically solar. Okay, so if suppose it's a solar power plant, so it's intermittent in nature. Whenever the radiations are changed suddenly, then it may impact the ramp rate of the controller. This is one of the challenges. Same for the, if you consider the reactive power, right? In the weak grid, if you inject, if you are injecting the reactive power, it will impact to reactive power. If the both the active and reactive power are changing at the same time, then uh, it may not follow that ramp rate grid code. So that is one of the challenge. Then there's a curtailment of ramp compliance may reduce the plant revenue. It means suppose the set point is already achieved, that is 100 megawatt, plant is running. Because of some reason, the set point is reduced to 50 megawatt. Radiations are fully available. Ramp rate is 10%. When again the 100 megawatt set point is provided, it will follow the ramp rate. Okay, when it, okay, you have inverter will achieve that 50 to 100 megawatt within a second. But because of the ramp rate feature or because of the ramp rate grid code, what will happen from 50 to 100, it may take more than it may take the 5 minutes, right? So to 5 minutes, it will reduce the overall energy. It will reduce the overall energy of the plant, and it indirectly uh, impact to revenue of the plant, because revenue is the main concern in the plant, because for that only that plant is uh, that EPC company or who is the owner, he's integrating that plant. for the revenue only. So this is one of the concern. Then there is a key dependencies like in India, we can say active the ramp rate is 10%. But in KSA, there is one requirement that sometimes reactive power should not follow the ramp rate. In India, we need to follow the ramp rate for active power also, reactive power also. But in KSA, reactive power, sometimes they are asking us that don't follow the ramp rate for the reactive power. Then there are few conditions like frequency deviation, voltage deviation. In India, yes, though there is a frequency deviation, though there is a voltage deviation, grid code says that we need to follow that plant should follow the ramp rate. But in KSA, if there is a frequency deviation, they are expecting plant to suddenly inject the active power to control the frequency, or suddenly inject or absorb the reactive power to control the voltage. Then, okay, next one is active and reactive power control. So grid code says that uh, plant should achieve the whatever set point receive from the uh, tertiary level controller and need to regulate it. And second grid code is that if once it's settled, okay, it's a big plant, right? 500 inverters, 700 inverters are there. It may possible that it will oscillate because maybe consider a PI controller is not tuned because of some reason or what. So it will oscillate at the set point. So it should not. So acceptable band for those oscillation is basically 0.5% of PI apparent power. It should not cross that 0.5% of PI apparent power. This is what the grid code is. So there are some other grid codes as per region. For example, for reactive power, in KSA, they are saying that okay, in India, if the plant in India, the maximum reactive power achieved is depends upon the power factor grid code. So what is it? So that power factor is 0.95. That plant should not cause the 0.95 power factor, and that maximum Q is decided by 0.95 factor. But in KSA, that maximum reactive power it depend upon is basically it's a grid code there. If the active power generation is more than 20%, then reactive power should maximum reactive power generation is 33%. If active power generation is less than 5%, the maximum reactive power generation is 5%. So based on this is the different grid code for KSA. Then again, if it may possible that sometimes we need to uh, curtail the reactive power to achieve the active power at the plant, because active power is generating the revenue, and to achieve that set point it may possible that it may possible that control should uh, curtail the reactive power. Okay, so then there are challenges like uh, suppose there is a lack of radiations, right? So it will not generate the active power. Then it should regulate the reactive. There one more challenge is regulate the reactive power for the weak grid plant where reactive power changes because of the active power change. It's again because of sudden injection, like in KSA, what we observe whenever we are injecting the sudden active power, or may we follow, or they may ask us to suppose ramp up the active power with the 50% ramp rate. For the weak grid, we observe that there is a large change in reactive power, so that is one of the challenge. So we should not, if the suppose ramp rate of reactive power is less, what will happen? It will slowly regulate that reactive power, because its ramp rate is less. So we need to manage that reactive power ramp rate when there is a disturbance because of active power change, or you can say external disturbance which is received from the grid. So these are the challenges. Then okay, then frequency regulation. Grid code mandates that power plant should have frequency regulation functionality. So those functionality is basically you can say frequency watt or droop control. And there is one more functionality, um, synthetic inertia. Okay, first we'll go to frequency watt. This frequency watt grid code is this frequency what function is required in Indian as well as KSA or any other, you can say Uzbekistan or US grid code. But that synthetic inertia functionality is not required in India. It is only that grid code is available. That functionality should be available in the plant only in KSA grid, as per the KSA grid code. So consider uh, So what is the advantage of frequency control basically? So frequency loop control advantage is, if there are number of inverter, it will distribute the set point to achieve the to regulate the frequency. Okay, whatever the delta P is required, that it will distribute among the available inverter based on their rated capacity without any communication. This is what the advantage of frequency loop. So consider there is a tertiary controller, there is a plant. Okay, and there are number of plants. So consider those number of plant are the inverter, and if there is a frequency deviation in the grid, so it is expected that all the plants should inject the delta P as per their uh, frequency, as per their capacity. So for that there is a grid code is defined. So for that there is a droop coefficient and frequency deadband. So usually in India the deadband is 0.03 hertz. In case it is 0.05 hertz, and droop coefficient is usually 3% to 7%. And as per the usually this droop coefficient should be 4%. 4% means whenever there is a change, 4% change in active power, sorry, 4% change in frequency, there is a 100% change in the active power injection. That is delta P is 100% basically compared to pure apparent power. So this is a typical frequency control diagram. Here we can see this is a dead band, and whenever the frequency deviates, it is more than or less than the dead band, it will either it will generate the delta P, and that based on the P set, we need to add that delta P and need to achieve the set point to control the frequency. Then the second functionality for the uh, second functionality is to control the frequency synthetic inertia. Okay, this synthetic inertia is not same as a primary controller what we read in the article, right? That synchron motor or virtual inertia generators like that. It is not like that. Synthetic inertia is basically required in KSA. What it says, it want plant to reserve the capacity. So that how much power need to reserve, that is defined by them. So consider it's a 10%, and whenever there is a frequency deviation, that power suddenly, without following the ramp rate, suddenly need to inject in the grid. So consider it's a 100 megawatt plant, reserve capacity is 10%. So though set point is 100%, you need to achieve the 90 megawatt at the PI, because 10% is 10 megawatt. So 10 megawatt need to reserve. And whenever there is a frequency deviation, now how will detect that deviation? That either that frequency deviation we detect by F measurement, or we need to consider the rate of change of frequency also. If it is more than as per the case limit, it is 2.5 hertz per second. If it is more, if the rate of change of frequency is more than 2.5 hertz, yeah, we need to release the complete reserve capacity. And whenever the frequency will come within the deadband, we'll again reserve that much of power and again achieve the set point 90 megawatt. This is what the synthetic inertia feature is. And second is voltage regulation. The voltage regulation, yeah, it's the same as a frequency control. Whenever there is a deviation in the frequency, oh sorry, whenever there is a deviation in the voltage, it will inject the delta Q. Uh, it will absorb or inject the reactive or capacitive inductive to control the voltage. So there are two functionalities. There are two functions include to achieve the voltage regulation. First one is voltage VAR, that is voltage loop control. Second one is AVR control. So same as frequency droop, in voltage control also voltage deadband and droop coefficient is defined. So again, the droop coefficient in all the plants, they are usually keep it 4%, and for voltage deadband it's a 2%. 2% of its nominal voltage. So during this there are few challenges, like it may possible that in the plant active power is already generating at its peak, so there is no much capacity available in the inverter to generate or absorb the reactive power to regulate the voltage, right? So these are the few functionality. Again, there is a weak grid. In weak grid, for small disturbance, there is a voltage swing. And if there is no capacity or capability of that plant to generate the reactive power, it will not regulate the voltage. So these are the few challenges. Then there is one more requirement of AVR. This AVR grid code, this AVR requirement functions is not included in the Indian grid code, is required in KSA grid code. So that grid code manager DR provide the voltage supports at POI. So whatever the set point is V set basically. Whenever this operation is enabled, whatever the V set is provided, suppose it's a 132 kV bus. So we need to, that controller or the plant should achieve that much of set point at the POI. So, okay, this is the PI controller. Based on the error, it will ramp up or, sorry, ramping is not required in this. It will increase or it will decrease the Q set point and it will achieve the V set. But consider in the plant, there is no reactive power support. Reactive power support means inverter are not capable to generate that much of reactive power because it's already generating the reactive power. What will happen? In that case, this error won't be zero and that PI controller will continuously accumulate the higher set point and it will continuously give higher set point till consider that POI apparent power, whatever the POI apparent power is. And because of some reason, if active power generation will reduce, that suddenly it may possible that the inverter suddenly achieve the higher set point and it may result in oscillations in the system or it may result in it will trip the transformer or anything is happening in the plant, right? So to avoid that, yeah, we know there is a well-known technique that is anti-wind up loop, anti-wind up technique. But if you use though we are using anti-wind up, yeah, it saturate the output, it saturate the Q set if measurement is not received. But at the same time, if there is a delay in the system, if there is a delay in the measurement, suppose there is a 2 second 3 second delay in the measurement, we may observe the small oscillation at the output of Q set. This is one of the challenge at the time of implementing of AVR functionality. So then there is a power factor control. This power factor okay, grid code is available in only Indian grid code, not in KSA or Uzbekistan or US. So it mandates that power plant should maintain the power factor within the 0. Plus minus 0.95 power factor. So there are different challenges like solar inverter cannot supply full active and reactive power because each inverter each inverter or different inverter makes maintain the 0.8 power factor at its PI independent of what is PI apparent power. Based on the active power, it is limiting the reactive power to maintain the 0.8 power factor. So this is one of the challenge. It has high active power output and reactive power capabilities. If it is generating the higher active power, then it will reduce the reactive power capability. So this is one of the challenge. Okay, now this we can avoid by providing the active power or reactive power priority in the plant. If the reactive power is a priority, what the controller will do? Controller will obviously reduce the active power generation to achieve that set point. Right. So it's completely depend upon what priority you're providing in which operation mode. Then it may possible that it is not meeting the PF requirement. It is not meeting the set point receive PF set point. Maybe because of other reason like there is oscillations in the system in the weak grid or what. So this is one of the challenge. Then okay, if there is no grid operator may ask the dynamic PF changes continuously. Sometimes it may say okay maintain 0.95, sometimes it may say okay maintain whatever the PF is. So it may increase the complexity of the plan. Then there is one more requirement, that is communication and control. So grid code mandates that large power plants should communicate and communicate with all the asset in the plant. So all the asset means we already discussed, right? Weather monitor system, then inverter. If in the plant there is a statcom, then yes, statcom. Okay, so it's functional to the SCADA integration. It should integrate with the SCADA as well as regulatory, whatever the tertiary control is there, right? Then it should communicate with the inverter to achieve the set point or to update the set point. Then it should continuously monitor the voltage frequency power, because these measurement it will receive from the pqm meters. So it should continuously monitor. But there are few challenges like a latency. If there is a high data is exchange between the product, that is that power plant controller, and in actual asset, there will be a delay in the system. So that delay, it may lead to delay in measurement may lead to, may possible may lead to, suppose controller is giving some set points 100 megawatt, but because of delay it receive only 99, because previous set point was 99. So it may possible that control will give higher set point, because it may think that okay, set point is not achieved. It may possible that few inverters are not generating the active power, or few inverters are not generating the reactive power. So to achieve that 100 megawatt set point, it may give 101. So this is the issue of latency. Suppose ramp rate is not following in frequency deviation, and if there is a delay, it may possible that it will give suddenly a higher set point more than the 100 megawatt, because in frequency scenario or in voltage scenario, it is not following the ramp rate. Okay. And one more challenge is that it should, that power plant should communicate with all the multiple all the assets or all the vendors available in the plant. So there is an inverter make, there is a SCADA, there is a EMS, there is a PPC. It may possible that all vendors have different communication protocol, maybe in rare case scenario. So that controller should have capability to interact with all the assets. Then and then if there is a need for the fast response while ensuring the robust control. So that fast response, uh, that fast communication, this is one of the challenge in the power plant. Okay, and then there's one more, fault right through. Now fault right through is basically uh, FRT defines the performance of inverter during and its post fault condition, and at the time that the power plant must remain connected to grid during that fault. So FRT is basically, it's a transient scenario. So it is expected that this FRT grid code should be achieved by the primary controller, not the secondary controller, because secondary controller time step was one, maybe maybe in second or maybe 2 seconds, and it is slower than the primary controller. So this is the functionality. This grid code should be achieved by primary controller. So grid code mandate that renewable power plant must have this feature. So basically, for LVRT, HVRT, that grid code is clearly defined, but for LFRT, HFRT, that grid code is not clearly mentioned. Okay, so there are few challenges like inverter-based resources. Mm, Basically, actually, the inverter, what inverters do, if there is a disconnection, if there is a suppose small disturbance, or it for the small disturbance also it will trip, right? So that's why this is one of the challenge. So in FRT, if the power plant have FRT function, it should stay connected to the grid, though there is a uh, though there is a dip in voltage, or there is a swell in voltage. Okay. Then large scale tripping in DR during the fault can cause the cascaded blackout. Then there is a weak grid. If there is a weak grid, again there is a small disturbance may occur because of higher injection in active power, sudden higher injection in active power, or maybe okay, it's a big plant, right? Maybe it may possible that one inverter is tripped suddenly, and because of that there is a sudden change in active power or reactive power. It may trip. So these are the challenges. And in this scenario, if voltage of that inverter goes below defined range, you should follow the it should activate the LVRT, HVRT, and it should stay connected to the grid. Then these are the few LVRT and HVRT requirement in the grid. Here you can see, if the as per the Indian grid code, if the voltage is within the 10%, it should continuously connected to the grid. But if voltage, suppose in LVRT case, if the voltage goes below 0.8, is between 10 to 15%, then it should stay connected to grid till 10 seconds. After that, if voltage is not recover, then it should trip. So same in HVRT condition, you can see if the voltage is more than the 30%, it should suddenly trip. But if the voltage is within 1.3 to 1.2 voltage, it should wait for it should, that inverter should stay connected to 0.2 seconds. If still voltage is within that limit, it can trip. This is what the grid codes are. Then there is one more grid code, that protection and coordination. Grid code demands that there should be proper protection system to ensure the safe operation and fault isolation without unnecessary DR tripping. So what it is? So it should include the function like over voltage or under frequency protection. Then there's anti-aliasing detection, means if grid is not available, that inverter should detect that grid is not available, and it should open its circuit breaker. Then there is a coordination with the grid protection relay. So there are challenges, right? Miscoordination. Suppose there is no coordination in the grid, and it may possible that suppose one inverter is tripped because of some reason, and there is a small if there is no coordination, what will happen? It may trip the other inverter, or it should not isolate that the faulty part. So what is the grid code say? Okay, if there is a fault in the specific inverter, just disconnect that part from the grid. Then there is a weak grid challenges. If in weak grid, if protection and coordination is not proper, it may possible there is a nuisance stripping risk, right? Continuously those inverters or maybe continuously those protection system will trip that part of the plant, and it may disconnect the inverter from the actual plant, and it directly impact to the revenue. So for that, the proper protection and coordination required, sorry, required. Then we'll go through the typical solar plant architecture. So in solar plant, you can see here the set point is received from the external source. So external source means controller. From the solar power plant controller, that PPC secondary controller, it will read all the measurement from the PKM meter, or it will read all the measurement from inverter or statcom. Nowadays, it is also expected that the power plant should control the capacitor bank also. The capacitor bank, they are connected to the grid for reactive power regulations. To So you should communicate with all the assets, and based on that, it will give P and Q set point to those inverters. So this is typical solar plant architecture. Then there is a flowchart for PPC, how the PPC power plant controller should operate. So PPC receive the set point from the external devices. Then it measures the inverter set points. It measures the inverter measurement, all the configurable settings. Suppose setting like what is the P apparent power of the, because it's a product, right? So if it's a product, same product should go all in all the different power plants in all the different regions. So we need to provide the settings, and need to define all the suppose frequency deadband. Frequency deadband is changed from uh, region to region. It is different for KS, it is different for Uzbekistan, it is different for India. So it detects all the settings, it detects all the measurements and PI. Based on that, it will calculate the set point. It will check the grid code guidelines, and if those set points or all the measurements, if all the grid codes are satisfied, then it will give set point to inverter. Otherwise, it will raise an alarm. It again calculate the set points, and then it will give to inverter. For example, suppose there is a reactive power. In case I told you there is a requirement that it should not cross 33% of reactive power if active power generation is more than 20%. So if reactive power measurement is going more than 33%, then what it will do, it will raise an alarm. Then the controller should reduce the reactive power set point, and based on that, it will give set point to inverter or statcom connected to the grid. Okay, so this is a basic flowchart for the PPC operation. Then inverter set point distribution. Okay, the primary objective of PPC controller is to achieve the maximum set point to achieve the maximum set point means maximum generation, active power generation from the plant. So, and the second aim is it should proportionally divide the set point to all the inverters so that inverter are equally loaded. If inverter is not available, okay, there is no issue, but it should proportionally divide the set point in the available inverters. Okay, so PPC controller use, okay, each inverter has its characteristics. Each inverter has PQ curve. So PPC is using those PQ curve points. Suppose there is six curve or 12 curve, right? 6 point or 12 point PQ curve. So so PPC should detect the maximum PImax and QImax. this J is basically representing to maximum available points. So from PImax and QImax, it will PPC will calculate the maximum active power and maximum reactive power that PPC can achieve at that instant. Okay, and based on this Pmax and Qmax, it will distribute the set point in the inverter. But in the actual plant, okay, it will propose to distribute the set point. But in actual plant, suppose there is a plant of 1 megawatt or 700 megawatt. Those power plant are in 4,000 acre or 6,000 acre. In 6,000 acre, it may possible that radiations, because of the cloud passing, radiations are available in one part of the plant, and radiations are not available in the second part. So in that case, PPC should redistribute the set point. If few inverters are not achieving the set point, uh, it should give higher set point to other inverters where radiations are available and should achieve that set points. Otherwise, what will happen? Otherwise, okay, in the power plant, basically they are calculating the PRs, performance review. So in the power plant, usually they are using the WMS meter. Radiations are already available. They are taking the average of the radiations, and they are calculating the expected P. And if because of redistribution that expected P is not met, they may raise a concern and there may be a penalty from the regulatory side. So that inverter redistribution logic is also required, and also need to consider whenever we are developing this inverter set point distribution logic. Then yes, second one is a child test environment for PPC validation. So we have one article where we provided few test results of PPC. So you can see this is a graphical user interface. It's a HMI, human machine interface, and this is the industrial PC where we put the PPC controller, Modbus drivers, and other files which required in the complete run. So from this HMI, the set points, the settings, and whatever the set configuration is required. A set configuration means inverter communication, IP address, and everything that is done by this HMI, and it is connected to the industrial PC. It is passing that information to industrial PC. That industrial PC is basically connected to the plant. But in our lab, we have using the Opal RT. Opal RT in Opal RT we develop the power plant. Okay, and in Opal RT will support the communication protocol also. So using the Modbus communication protocol, we're communicating with the industrial PC. And yes, so this is the complete setup. In this setup, this setup is of 20 megawatt we consider, and there are 8 inverters, and the maximum active reactive power capacity of each inverter is 2587 kilowatt and 1725 kVR. We'll go to the results. So this is a SL test for PPC validation. So this is okay. This test is carried out just to check whether the PPC is following that PQ curve or not. So we consider that okay, each inverter, though apparent power is we check, right, though after apparent power active power maximum active power capability is 2587 and reactive power capability 1725, we limited the PQ characteristic maximum PI to 640 kilowatt and 640 kVR, and initially we give some higher set point to 6 point set point, that is 6.4 megawatt. So as there are 8 inverter, so expected expect PPC is distributing this set point in uh, okay, the expected active power generation from all the uh, from each inverter is 800 megawatt, but as the capability is maximum capacity is 640, you can see that it ramp up, it follows the ramping rate, it reach to 640 in each stop. Then we change the set point to 4.8 megawatt, and you can see for at the it ramp down, it achieve the set point again. And same we validate with the reactive power also in both lagging and capacitive reactive power. So this we can observe. These are the basic test results from the PPC. Okay, so PPC have frequency loop controller. There is a dead band is defined, and initially the set point of the PPC is 4 kilowatt. When frequency is lies within the dead band, the PPC does not change the set point for the does not change the set point for the active power. But when frequency change or frequency is observed, then PPC start giving delta P, Okay, as per the Indian grid code, it follow the ramp rate. So yeah, it is ramping down and it achieve the final set point to control when the frequency again over frequency is observed, again the frequency is changed, it again ramp down and achieve the set point. And when the frequency start decreasing or it start decreasing, okay, active power generation is again start increasing. When it reach to dead band, it again achieve the achieve its set points. Okay, and same you can see for under frequency scenario. uh, Sorry. Okay, sorry. Hmm. So this is the reactive power control mode for voltage drop control, and same we validate in react for voltage drop also. Uh, Whenever the voltage will go above below its dead band, you start injecting the reactive power to control the voltage. And same when voltage will go above its nominal frequency, or it crosses the upper dead band, that reactive power injection start reducing. So this is what we can observe from the results. So next and last topic is basically typical power plant topology used in the large power plant. So here we can see, suppose, okay, the maximum transformer capacity I observe on the site is basically 270 or 250 MVA, and in the plant there may be 1 gigawatt or 2 gigawatt power plant or 2.4 gigawatt power plant available in the system. So if the maximum capacity is of 250 MVA, we can say that to to generate the 2 gigawatt, it may possible that there are number of POI connected to the same bus. Okay, so here I just for the example, I consider the two buses. So there are two POI, and for okay, if there is only one controller, then we need to add this. If it want to achieve the active power at this bus where the grid is connected, and for that we need to add this POI1 and POI2, and based on that, based on that the this is the total PIP measurement for the controller, and based on that it will achieve the set point. Then consider these are the two picom meter of both the PI. There is a transformer, and these are the different inverters. Okay, so consider these are the inverters. This inverter HG1 and HG1, and this is HG2, basically MFM3. Okay, it is connected to PI1 through the circuit breaker, and yes, and this HG2 and this HG2 MFM4 basically connected to PI2. And initially these bus coupler are open, this bus coupler logic is not required, and it is achieving, and whatever the set point is giving, it is achieving. But consider, because of some reason, this circuit breaker is open, or there may be a issue in this secondary winding, and this circuit breaker will open. But what is the expectation from the power plant? The expectation is it should achieve the maximum active power from the plant. So what the power plant is asking, just close this bus coupler, then there is a PV inverter. Then okay, if consider the rating of this transformer is 250 MVA, then we can say that okay, the rating of this all PV inverter is 125 and 125, and addition of 125 and 125 is 250. So if radiations are less, this CB is open, radiations are less, bus coupler is closed. So the expectation is controller should give set point to this HG1 and HG2 such that it should not cross 125 MVA. If okay, radiations are already available, then there is no need to give set point from HG1, because you can already achieve the highest set point from the HG2, but radiations are not there. And if the plant want to achieve the maximum active power, then yes, it need to limit the set point of HG1, HG2, and need to give set point according to that. And same for this part of that. So this is a typical power plant topology using the uh, large scale power plant. Then okay, so takeaway summaries: large scale renewable power plant face the multiple grid core challenges. So these challenges rise because the inverters based renewable are not behave same as a synchronous generator. Like synchronous generator have its own inertia, right? It's control the frequency, but inverter, okay, they are basically VNF control, but inverter are basically working in a PNQ controller. They are not grid forming. So this is one of the reason. Then to address this challenge, it is necessary that those renewable power plants should support the grid stability and reliability. So ultimately, ultimate aim is to overcoming these grid core challenges. Uh, to overcoming these challenges, it is necessary that power plant should follow the grid code, and yeah, secondary controller and smart algorithm enables this compliance and resilience. Okay, thank you. Thank you all. Any questions?
Uh, Thank you, sir, for your valuable insights under this topic. Any questions? Any queries? Please ask.
Okay, if you have any doubt regarding how actual plant is working, what software they are using, so you can ask. Not about this one, but yeah. Okay, thank you.
Any questions? Okay, thank you very much, sir, for your deep insight on this topic of different grid code challenges for large-scale renewable power plant operations. And thank you all the participants for your cooperation. Thank you very much, sir.
Yeah, thank you. Thank you all.
Thank you very much, Dr. Ajinkya. And I would like to say to all the participants that if they have any questions, they can send it to us, and we can forward it to the speaker for his reply. So anytime you can contact us. Thank you very much for joining. And thank you very much, Dr. Ajinkya.
Yeah, thank you. Thank you.
Okay, thank you. So we can close this meeting now. Thank you.